So this week's presentation is going to be the last for this section, or for this course rather, so there's nothing new that's going to come in after this, just a reminder on that. What we want to do this week is look at life cycle assessment as the main topic. We're also going to cover some very basics on carbon footprinting rather, as well as water footprinting, and how these are the same or similar to life cycle assessment or the differences that we find in these. Just to note, this is not covered in the textbook, so you're only going to rely on the material in these notes for this week. So we're going to start on life cycle assessment. So LCA, that is life cycle assessment, what exactly are the characteristics of these? So it is the process of evaluating the effects of a product, process, or service that it has on the environment. So what that means is that it is a quantitative method or a tool that's going to give you a number. So how bad is my process? So not good or bad, but what is it exactly is the number, a number associated with environmental impact of my process. It could also be a product, as we say, so it could be 1 kilogram of paper, a piece of paper, 1 liter of biodiesel, something like that, or a service. So what is the impact of dry cleaning, for example, or some other service that you can think of. Jumping to the bottom here, it is a life cycle, so it actually, in its proper terms, is related to the cradle to grave. So a cradle is like a baby has a cradle, it's at the very beginning. So on the left-hand side of our flow sheet, the cradle is going to be raw materials or anything that comes from the earth. And on the right-hand side of our flow sheet, the grave is the very end of the product. So it's not just the use of the product, it can also include, sorry, not just the manufacture of the product, it will also include the use, the disposal, the recycling, all the way back to the grave. So it's going into landfill or incineration or something like that. Okay, that is a proper life cycle assessment. It's spoken about as a cradle to grave. You can get examples where it goes cradle to gate. So gate will be on the right-hand side of the flow sheet up to the end of a product that's manufactured. So it'll be 1 liter of biodiesel. It won't be the use of the biodiesel, for example. Or it could be somewhere to some intermediate. So it might not be all the way to the left. It'll be, all the way to the right. It'll be somewhere as we go along. We'll see a flow sheet on what exactly I mean for that. You can also do a life cycle from gate to gate. So it'll be just for your site where you work on one day. So you get into your factory, you get some sort of oil. You then produce biodiesel from that oil. So you only look at the facility from your factory gate to your factory gate, not how did the oil get to you and all of that. Strictly speaking, by the standards, these are not life cycle assessments, but you use the same methodology for that. Okay. Life cycle assessment, as we said, is cradle to gate. So coming to the middle here, what that means is it is the transport, distribution, use, reuse, maintenance, recycling, and final disposal. It's everything in the value chain for that product, process, or service. Okay, so the flow sheet that we're talking about. So if we look at this in terms of a block flow diagram, where each block represents a particular site for a factory or an industrial system. So let us use that example of biodiesel. So in this block, I make biodiesel. So for that biodiesel, I have oil that comes in and I have biodiesel that comes out. So it'll be 1 kilogram of biodiesel, 1 liter of biodiesel or something. Everything in a life cycle assessment is going to be related to some normalized value. So we're not going to worry about, we do worry about it, but typically we won't say it's a life cycle assessment for 3,331 liters. We normalize it to a useful number. So coming out will be our 1 liter of biodiesel, and everything else that goes in we'll look at in a moment. And out, these are the things that are going to cause environmental harm. So it's going to be solids, liquids, and gaseous wastes, as we've discussed in previous lectures. Because this is cradle to grave, we need to go all the way back to raw materials. I've said that our box is biodiesel, where we've got oil coming in. You can't pull oil from the ground. You have to get it from somewhere. So that's going to come from, sorry, let me click properly. That's going to come from somewhere else. So oil is going to come from an oil manufacturing facility. Our biodiesel doesn't just come from oil. We might have some chemicals, and I'm just using a limited number of boxes here. So there's some chemicals coming in. There's a chemical. There might be electricity that comes in. Electricity doesn't come from the ground or just from magic as well. We need to get that from other places. So electricity, if we just carry on concentrating on the top block, that comes from something like coal. The same thing happens for these oil things. Oil doesn't come just from the ground magically from oil. Yes, there's some processing. It comes from the farming of the soya beans or the collection of this. That's why the 2 blocks, maybe it comes from the collection of some oils from a restaurant, for example. These boxes could also represent things like transport, so we actually need to transport it. So what are the transport issues related here? We will do this back and back and back all the way up until we have raw materials that we've mined out the ground. Okay, so we might go far back or not. On each of these boxes, we now need to calculate how much for our 1 kilogram of biodiesel are we going to have the solid, liquid, and I see I've missed this box. No, I haven't missed that box, sorry. All of the red arrows are representing the solid, liquid, and gaseous waste. So for 1 kilogram of biodiesel, if we can go back all the way to whatever this one is on the far left here, how much solid, liquid, and gaseous waste is there being produced for that 1 kilogram of biodiesel? This diagram here, sorry, I've jumped now. This diagram here is going to be the full life cycle of the process. It's also going to include, and it's just my last click here, it includes things like recycle. So we said it's not just the use, there might be recycle. So on our biodiesel plant, we might make some wastewater. The wastewater then gets recycled. We take that into account. So recycling is a good thing for the environment, but there is still going to be some waste. Probably less waste than if we didn't have this recycle stream on it. That now, I jumped ahead a little bit, sorry. So that now forms our border, or our, what is the boundary rather, of our system. Okay, this sort of system here is very simplified. So if we look at it more realistically, there are going to be not just 5 or 6 boxes here, there are probably going to be thousands of boxes when you start thinking about where everything comes from. The other problem is that we've said this top one here is electricity. Electricity doesn't just supply our biodiesel plant, and I'm just using electricity here, but I probably should use the word energy, so there might be a different box here for natural gas, renewable energies, whatever those might be, nuclear, all of those. So electricity doesn't just supply our box, it supplies everyone. So this now becomes a very integrated network of everything connected to each other. It's also going to include recycle for various other things, probably all of them, not just the ones I've highlighted. So everything probably has their recycle. So to get this sort of flow sheet isn't going to be simple, and that's why sometimes people drop off and say, okay, let's just drop off a little bit easy, and we do the life cycle assessment for the right-hand side of the graph, or the left-hand side, or a portion. Okay, you'll see the reason or why or how that becomes useful in one of the later slides. So just some more characteristics of an LCA. So it's not meant to be a tool to replace other environmental tools. Sorry, that's bad wording. It's supposed to complement them. So it's not going to replace things like an EIA, so environmental impact assessment will still be undertaken, but what a life cycle assessment can do is that it can give a number, or an actual quantification of how bad just the number for what the EIA impacts are. So if you go to a meeting or one of these stakeholder engagement meetings, and then you say, this is the option for the EIA, and then a stakeholder engagement okay, but what happens if we swap this out for that? LCA can be the tool to quantify the difference between option A versus option B, or what happens before you do the change versus after you do the change. Because it is a quantitative tool, so you're getting a number out of it, it's trying to avoid things like fossil fuels are bad. So we say fossil fuels are bad, but how bad are they? Is 1 bad, is 2 bad, is 10 bad, or how bad is bad? So it also looks at organic. People sometimes say that organic is better, but how can you actually prove to me, show me that why is organic better? Organic might use more land, you might be using more water, you might be using more a whole lot of other things because you are not using the pesticides and you don't get as high a yield on your crops. So maybe it's actually not better. So what it means, what LCA does is it looks at it from a numbers point of view. So what are some of the applications of LCA? If you live in the UK and if you go to somewhere like Woolworths, the Woolworths equivalents over there, and you go to the orange juice and apple juice sections of the shopping center, when you pick that up and you turn it around to look at the back of the pack to see the information on it, like South Africa, you'll see the information about the sugar, the fat, the calories. You might see something about vitamin A, vitamin B, all those sort of things on medicines. But they do also have a section where they tell you the information of the life cycle assessment or the environmental impacts of the product that you're looking at. So I'm not quite sure how many products they have in the UK at the moment that they do this to, but I know the number has been increasing. And this has been on their product since about 2010 or so, as I recall. So the idea of this is that if you pick up a 1 liter thing of orange juice or a 2 liter pack of orange juice, you'll see what the differences are. Typically those will be fairly similar because the only difference is the packaging. But if you see brand A versus brand B, one coming from South Africa and the other one coming from South America, they're going to be different farming practices, different transport, different everything, so those might be different. It's also important for them, or if you're looking at, do you want to rather buy apple juice or orange juice, one might come from Spain, so it might have a much lower impact than the apple juice, for example. In South Africa, I haven't seen that anywhere yet, but there has been talk about doing that in shops like Woolworths, and not just on apple juice and things like that, but a little bit broader than that. So that's one of the areas where you and I might see actual LCA results communicated. On a more industrial side of things, particularly for when you become engineers one day, if you are looking at process design, so you want to check, is furnace A better than furnace B, or do you want to have a distillation column versus some other sort of separation technique, you can do an LCA at that stage. For the process design, and in the same way, a process improvement if you've already built the plant that you're going to be working on. Similarly, if you look at the development of business strategies, what this means is if I'm a very rich businessman and I've got a few billion rand to spend, if I want to buy some plant, if I want to buy a Sasol, for example, if I can ask them for the LCA, I can see what sort of environmental impacts they have, and is this a good idea or isn't it a good idea? Eco-labeling is fairly similar to what I've said about in the first part about the orange juice, or product policies. There are some policies that might say, let's just say, for example, you can't have a product that has an LCA score above a certain number. Or if we have purchasing decisions, that's the same as I say for the top, but not just for consumers, but for anyone. And that obviously leads to development of different lifestyles. Am I now an orange juice drinker instead of an apple juice drinker? I've already said that LCA is product orientated. So why would we use it? So it's not just product orientated, it's also process and service orientated. But because of this product orientated nature, it makes it slightly unique over some of the other environmental tools around. So EIA and some of those other tools look at the whole process and what would happen if I put something somewhere, or what's the impact of the entire site. LCA can look at a single product as well. So if I am Sasol and I have both petrol and diesel and kerosene and all sorts of other things, I can work out my life cycle assessment score just for petrol or just for diesel. So I can break it down by various techniques so that I know for one single product, not for the whole process. So as those other points say, so there are other environmental assessments which can look at a whole process or individual components. LCA can look at the whole chain, not just a single component. So LCA can look at an individual component, but looks at the whole picture as well. LCA is also integrative. So what that means is that it's going to include all of our environmental impacts into one single tool. So it's going to look at it, it's integrating the environmental impacts of the solid, the liquid, and the gas, and it's going to get us a set of numbers that represent all of those different impacts. We've already said it can focus on a product, a process, or a service. It can also partly, and this is a bit of a changes as the method develops, it can potentially look at some geographical information. So it's not very specific, but it can consider certain things, and we'll get to that as we go through these slides. It also takes into account some negative impacts. So while there are some things that you can do as an engineer to potentially fix, or in your mind you think you're fixing an environmental problem, it may be a negative impact. So recycling may not always be the best way to go, and maybe recycling is a bad example here, but let's rather replace recycling with something like incineration. That might make a little bit more sense to you. Incineration is going to reduce the landfill waste that we might have. But by reducing the landfill waste, what we're now doing, or potentially doing, is we are creating more air emissions. So what we've done is we've solved a problem for solid waste, but we've increased our air emissions. So life cycle assessment will take that into account and see, okay, well, if we do a landfilling option, or if we incinerate, we now have the trade-off between solid waste and air emissions. Which one would actually be better? A key factor that I've already brought up here on why you would use life cycle assessment is that it's quantitative. So quantitative meaning numbers. So I'm not going to sort of go and say, I think this one's better because everyone knows that this is better. No, not everyone knows this is better. It's going to use numbers. So because it's using numbers, we are trying to avoid the emotion or the feelings. So I don't want to go into this thinking that biological is better, so that means that I must go the biodiesel route and not the typical diesel route. We're going to be doing numbers. Because it can use the numbers, The idea on this is that if I do the numbers, if you do the numbers, if we're all using the same set of assumptions and the same set of data, we should all come up with the same result. So it's not going to be that we come up with numbers based on our feelings. Okay. So because it can be used to represent various parts of the life cycle, so that's the transport, manufacture, use, and recycling, and the whole thing, this is all going to be quantitative. So I've already mentioned some of the uses of this, but just again to understand why we would do life cycle assessment. As I've said already, it's to understand the full life cycle. It's also to understand the impact of my company's role in the full chain. So I might be making hamburgers for McDonald's. I know what my impact is as McDonald's franchise somewhere in Randburg. But something called the chain of responsibility or product stewardship now comes into play, where I want to be responsible. And if I look at my life cycle, I want to know, where am I getting my lettuce from? Where am I getting my cheese or my hamburgers from? So product stewardship is the process of looking at where the things that I get, where are they coming from? Or the things that I'm making, where do they go? So it's a chain of responsibility. So something like a plastic manufacturer is going to be interested in knowing where does his product go after he's made the plastic, who's doing what with the plastic so that they can then recycle it. So life cycle assessment, we can then look at the full chain, and not just from a chain of responsibility point of view of, is that the right thing ethically or morally to be supplying or to be getting my lettuce or my hamburgers from that supplier, but I can also see this in terms of Company A supplying lettuce versus Company B supplying lettuce. Is the one being more environmentally friendly than the other? And life cycle assessment can be that quantitative tool to actually determine that. So if we look and break this down into who uses LCA in terms of industrial or governmental type rules, I've already mentioned some of these things on industrial uses. There's product improvement, design. We might even come up with company policy or just product information. It also comes into play with marketing strategies. So I know from my own work, so just to let you know, this is life cycle assessment is my research area for my postgraduate students, that places like VW, or companies rather like VW, BMW, they have life cycle assessments for every single component in every single car that they've got. VW, I know I've seen these numbers before. I've seen presentations where they can tell you that the 2020 version of whatever car they're trying to sell has a life cycle assessment score that is 5% better than the previous model, or 10% better. And then they can compare it to different other products that they've got as well. So they can say that the Golf is better than the Audi, or the Audis were better than the next one, and they can improve it on that. So they use the marketing strategy, use the LCA, for their marketing strategies. One of the issues with LCA, and I'll maybe mention it now, it'll come up again later, is that a lot of the information here is very sensitive. So in an LCA, to get the LCA, you need a lot of corporate information that's very sensitive. So it's going to be very difficult to compare the LCA of a VW to the LCA of a BMW, because it's not necessarily going to be comparing the same thing. And we'll get to that later. For government, why would government be interested in LCA? Particularly for eco-labeling, so things like you must put things on your orange juice to tell me what the life cycle assessment scores are. It might be for a deposit refund scheme. So there's been an example, I've seen work being done where if you have your 1 liter Coke bottles, the glass bottles, what is the actual environmental impact if we put a 50-cent tariff on a bottle and ask everyone to return their bottle for a refund or the deposit back for that refund on the deposit bottle? Or if we just sell the bottles, we just say, okay, you keep the bottle, you do what you want with it, and then you recycle it on your own. So what would the environmental impact of the two systems be? So at first guess, you would say that obviously if we can put a deposit on that, everyone's going to now go to a central point, and they're going to put their glass bottles in a central collection bin. There's going to be money involved, but we've collected all the deposit things from a central point. But not everyone's going to do that, and even if we don't have that deposit refund scheme, maybe responsible citizens would still recycle their glass. Okay. Taxation here, this is simply related to if we have a high LCA score, you need to keep your score under a certain limit. This one I've put in here more for the carbon footprinting, when we'll get to that a little bit later. For NGOs, so non-governmental organizations, typically here what happens is this is to supply consumer information. So the very common example in LCA of how it's used is it better to have plastic or paper carrier bags when you leave your shops? So an NGO might look at it saying, okay, well, we've seen the study that says paper is better or plastic is better or something else is better. So then they put out information and they push government or they push industry to say, okay, well, we've seen all these studies. Why don't we swap and reduce the plastic and make it paper rather? Those sorts of assessments. And you can see that's why I mean influencing enterprises or governments. For you and me, we are probably never going to see an LCA in our day-to-day life unless it's brought into the orange juice, apple juice examples. If you're in Europe, it can influence buying power. So if you see that there's orange juice that has a terrible score versus orange juice that has a good score, you are going to start buying the one that has the better score, or potentially depending on the cost of the two. If we start buying one brand of orange juice because it has a better LCA score, then it's going to lead to us as consumers influencing market through our buying power rather, so it could potentially influence the producer into making something environmentally or more environmentally friendly. There are, however, several problems with life cycle assessment, and you probably guessed on some of them from what I've said so far. The first one, however, though, is that they can take a very long time to perform. So I've already said that I've got students, this is my research area. I've had students in the past, and I've even got one as we speak now, who is looking at the life cycle assessment of some sort of product. That life cycle assessment is expected to take 2 years to perform. So if we are doing an LCA, if it takes 2 years to do the LCA of one single product, it's going to take us millennia to actually get LCAs of everything to get us to a point where we can compare orange juice to apple juice. The one thing with LCA, though, is that because I've now done it for 1 liter of orange juice, to then do it for 2 liters of orange juice is fairly easy. So we can jump from one packaging system to the other fairly quickly. The other route to solving the time problem is that we can do them very quickly. So it is possible to do an LCA in much less time, but the problem with that is that the data that we collect is often not reliable. So because I've said this data, some of the data that's in these LCAs is corporate data or sensitive data, companies won't give us that data. So the way around that is to just estimate it. So I can estimate anything in 5 seconds and just thumbsuck something, and I can get an LCA out in 20 minutes. But what's the reliability of an LCA that comes out in 20 minutes versus one that takes 2 years to do? The next issue is that an LCA that is valid today may be invalid tomorrow. So particularly with things that are changing very quickly. So BMW makes a 2020 model car, they do an LCA on it, but next year they've got a different model car. So now that LCA is no longer valid for the 2021 model car when they did it on all the 2020. So anytime you change anything in your entire life cycle, as we had on that blue block diagram earlier, if one thing changes on that diagram, the entire life cycle assessment has to be repeated for your product. So if I'm making my biodiesel and suddenly my farmer all the way down at the beginning of the chain decides to change his fertilizer and use a different fertilizer, the LCA that I did 2 days ago is now not valid anymore. The same thing is true if we have an LCA in one area versus another. So if I do an LCA and I tell you that the impacts of biodiesel in South Africa are some set of numbers, that is not going to be true in even somewhere like Namibia. Because in South Africa, we might have a different electricity mix, we might have different water problems or issues. So you can't necessarily say that just because I got an LCA of one value, it's going to be valid for any other system. This next point with fast-moving technological advances, so this is similar to the second point with things changing so quickly, the comparative LCAs also become outdated fairly quickly. So I can't necessarily compare my biodiesel to my competitor's biodiesel because mine's changed, theirs changed. It's not always the same. So that is one of the problems with the LCA scores on the orange juice, or have the orange juice the manufacturer of the orange juice has everything stayed the same since that was done. Why it's probably still on orange juice is that orange juice is a fairly small block flow diagram. It's going to be growing your oranges, squashing your oranges, and transporting them along. It's not a highly complex problem like a BMW or a car, rather. So to make a car, there are going to be thousands of screws and bits of metal and paint and all sorts of components that go into that. Orange juice is a lot more simple, so it's probably not going to be outdated as quickly. One of the problems that's listed here that I've seen in textbooks all over the place before, but I'm not quite sure how how valid it really is that there is also an idea that it can hinder technological advances. So if your R&D team is saying that we need to do an LCA before we can proceed with this process, even waiting 2 weeks, 3 weeks, 3 months is too long for certain high-tech advances, particularly in the electronics industry. So if you aren't going to be moving forward without an LCA, this will hinder your advancement of the technology. I've not necessarily come across this before, so typically the LCA will go ahead and then we'll do the technology will go ahead, we'll do the LCA afterwards. You can make tweaks to the product afterwards, but I can clearly understand why this might be a hindrance if there are limitations to you can't do the process, you can't make the process until you have life cycle assessment data. Okay, so I'm going to stop there and start talking about something slightly different now. So I said we're going to have carbon footprinting and water footprinting. So let's just come and chat a little bit about the carbon footprint. So what a carbon footprint is that it is actually a subset of, or it can be seen as a subset of life cycle assessment. At the end of a life cycle assessment, we are going to have a set of between 10 and 20 numbers. So there are going to be different categories depending on whether it's water, solid, liquid, or gaseous emissions. And we're going to have certain categories that say, for this category, the number is this, that. One of those categories in LCA is global warming potential. So the global warming potential looks at the life cycle impact of carbon dioxide, carbon monoxide, methane, SF6, and a couple of other aspects. If we do a life cycle assessment on the global, or we look at the global warming impact category of a life cycle assessment, that is a carbon footprint for scope 3, a full extent of the carbon footprint. However, carbon footprinting is divided into 3 different scopes. There's scope 1, scope 2, and scope 3. So what that means is that in our facility, if we are looking at a scope 1 assessment, we are only going to be worried about the impact of our site. So what air emissions are we letting off from our site within our site boundaries? So that's all we're worried about in carbon footprinting, scope 1. So it's not going to look at any of the solid or the liquid emissions, just the gases. And not all the gases, just those that contribute to global warming, so the greenhouse gases, the GHG. In scope 2, you would look at all your emissions, but then you would look at anything any energy that you have on site, any of the emissions due to your energy. So if you have electricity, how much electricity are you using? What are the emissions what are Eskom's emissions because of your electricity consumption? The same thing for heat or steam, natural gas, or anything that is energy related. So if we are getting heat from natural gas, what is the contribution? That would then be scope 2. Okay, scope 2 is actually scope 1 plus, so scope 2 is everything I've just mentioned now, plus the direct emissions. So to get to scope 2, you have to add scope 1 as well. So the same thing with scope 3, you would add scope 1, scope 2, and scope 3, which now includes everything else. So everything else would be everything like we just explained it in the blue box diagram for a full life cycle. So from the cradle to the grave. So everything from the cradle to the grave, we look at your site and we say, what are you producing? It's again 1 liter of biodiesel or whatever it might be. For that site, plus everything before it, how much carbon dioxide, carbon monoxide, methane, SF6, and some other chemicals are you releasing? There is some maths involved, which we'll get to later. What exactly are you releasing? And that would then be a carbon footprint. Typically, it's not done per kilogram of product, though. It's done per site. So what is your impact as Sasol? What is your impact as Nedbank or something like that? So it doesn't necessarily come back to a single product or something like that. Carbon footprinting, from what I've seen as well, is often more a business tool and not necessarily something in the chemical or metallurgical, sort of a technological processing field. So often it's looking more at what is my impact due to travel. So someone like Nedbank doesn't necessarily have any chemical processes, but they might look at their carbon footprint because of their heating requirements to keep them warm in winter. They fly around, before COVID at least, They flew around a lot to Cape Town, Durban, wherever else they might go internationally. So what are their emissions from their air travel and things like that? So because it's more a business tool, LCA is typically favored in terms of process engineering, whereas carbon footprinting is more a business tool than a process engineering tool. The other thing is that it is also governed by its own set of rules. So it has its own way of doing things, and you'll see in a moment there is the ISO, the International Standards Organization body, which sets rules for all of these tools. There is a separate set of rules for carbon footprinting. In the same way, water footprinting is going to have its own set of rules. So what we have in life cycle assessment is that it's going to look at typically the impurities in the water, but it doesn't always take into account the full volume. So this is a difficult slide for me to talk to, because if I'd given you this slide 5 years ago, this is 100% true. What has happened recently though, or it's maybe 5 years recently now, is that there is a new set of guidelines, the ISO 14046. So the ISO 14046 is a method on how to take into account the water footprint or the water use in a process. Okay, so because of this set of guidelines, LCA has actually modified their methods, and we'll get to it later, but there are actually different methods on how to do the actual numbers later on, and some of those methods now include the volume of water in the LCA. All of the LCA methods include the impurities in the water, but not all of them include the volume of water that is used. Okay, so I'm just trying to see water in LCA is accounted for in the inventory, but not in all the impact categories. So it might not be taking into account all of the water properly. So as I say, ISO has developed their own standards. So what happened was, because water wasn't fully taken into account in LCA, say 5-10 years ago, there was a group that was headed up by Arjan Hoekstra, and you'll see his name coming up in many of the references from now on. So Hoekstra and his team developed their own guidelines on how to take into account water, or they called it the water footprinting technique, how to take into account a quantitative means to determine how much water you are using on your site. This does go beyond water footprinting. Mass balance. Water footprinting goes beyond a mass balance, and you'll see that shortly. Okay, so water footprinting, I'm just trying to see, I think I've actually covered most of this stuff. Okay, so the Hoekstra, so there's the names, the spelling down at the bottom here, you can see his method at waterfootprinting.org. What Hoekstra and his team have defined the water footprint as is you start by defining 3 different types of water. So firstly, there is going to be green water, and that is clean water from the environment. So that could come from rain, rivers, probably not the ocean because that's salt water, any other natural water resources. So that includes going into a river as well as going out of a river. Rain also includes evaporation, so there might be evaporation involved here as well. Blue water is chemically purified clean water. So anything that you get, the simplified version of this is that anything you get out of a tap is classified as blue water. Anything you get from nature is green water. So these flows can be both positive and negative because you're taking them in and you're getting rid of them. So any clean tap water that you get in, you might put tap water back out into the environment. These 2 numbers here are absolute numbers. So you can actually go and put a flow meter in and you can calculate the green and blue water. Gray water is termed a virtual water, so it's not a real number, and we'll get back to what we mean by this on our next slides. The water footprint method also defines 2 things so that we take into account the full life cycle as well. So we first have the direct water, and this is going to be water that's used inside the system. So anything that is on my site is direct water. So this one in our blue box diagram from way back when, that very first blue box, would be direct water. That is on my site. I have control over that water. That is direct water. Indirect water is anything that somebody else uses. So I don't necessarily have control over people outside my facility. That is the indirect water. So if we come and look at the definition and how we calculate the blue, green, and gray, we'll start with the blue. So as we said, that is the volume of water, and it's going to be the volume of water consumed from ground and surface water resources. So again, this is the clean water that we've now purified, but notice here that it's only the water that is consumed. So if we have, and I'll use this just for the example here, if we have a big body of water to our side, to the left here, and we have some sort of facility in this opening here, we build our factory over here. If we take this water out, we then use it and we put it back. That does not count. We did not do anything with that water. So you might take in some water for cooling, nothing happens to that water, you just drop it back in. So blue water, remember, is that we've purified. So this would come from Rand water. It's very rare that you're going to take clean tap water in and then give it back to Rand water. So you're probably consuming almost all of your blue water, should I say. So that is going to be the, where are you going to lose this now though? So you've taken that blue water for your site, you're going to use it through evaporation. You might lose some due to incorporation. So this footprinting technique, I forgot to mention that earlier, the footprinting technique was actually developed by agricultural scientists. So this was mainly developed for somebody like an apple farmer. So if we are taking water out of the tap, we are irrigating our land. Most of our product is in the apple is water. So that's what we mean by incorporation. Your water that you took out the tap has now become part of your product. So it's become part of the apple, part of the orange. Okay. The last part is lost return flow. So any water that you took out of the tap that doesn't go back to the original source, that is lost, that is also part of your blue water footprint. Okay, so that is all the purified water. In the same way, green water footprint is now the rain aspect. So any green water that evaporates, so any rain that you get is effectively free, that would then run off, but anything that you then take, or because of your activities on your site have changed something. So water might evaporate, water might be incorporated again. So that again is absolute number. I can put a rain gauge out, I can measure how much rain comes down, there are ways to calculate evaporation. I can physically measure these numbers here. So these are true absolute numbers. The last one, though, we said is a virtual number. So gray water footprint is, don't worry about the text right now, let me rather talk and I'll come back to that. It is a virtual number. So how we calculate this is we look at how much dirty water or polluted water does your site throw away into wherever it might be. Okay, so this is a very terrible one. It looks like it's going into a river. What the gray water footprint is that if you are polluting something, before we polluted it, what was the concentration in our lake, in our dam, in our wherever we are sending this dirty water? What is the pollution there? If I have to take a 100% clean stream of water, so there's zero pollutants in that water, I have to mix it with my dirty water, and then from a mass balance from those two streams, I then end up with a stream that has the same concentration in our river. So our river is obviously going to have some pollutant. It's never going to be 100% clean. We are using an assumed 100% zero pollutant water stream that I'm now adding here to the left of this. You can see how dirty this water is. Most lakes and rivers are fairly clean, so the volume of water that we are going to have to add here is often thousands of times bigger than this small stream. We don't physically add that water. That's why we call it a virtual water. So it's theoretical value of how much clean water would we potentially have to add to this dirty water to then make sure that wherever it goes is clean. The mathematical formula to calculating that would be the water footprint of the process for the gray portion being the load, so that is the amount of dirty water going in, divided by the maximum concentration in our stream minus the natural concentration that's actually going in here. We talk about the maximum concentration because somebody might ask me, well, what pollutant are we talking about? Are we talking about BOD, COD, phosphates, nitrates, sodium? I don't know what pollutants we've got in here. We might have arsenic. Who knows what else is in there? We take the one that is the most pollutant. So you'd actually do this if you don't know, you would do this calculation multiple times for every single pollutant in your stream. So you do it for sulfate, for nitrate, one calculation for sulfate, one sulfate for one for sulfate, one for nitrate, one for BOD, one for COD. You do it many times. Whichever number comes out the biggest, that is the one that you use. So that's why we talk about the maximum concentration. It's going to be the one that leads to the maximum, the biggest pollutant in our stream. If you have a blue water footprint plus the green water footprint plus the grey water footprint. That gives you the total water footprint for your site. In 99% of the cases I've come across, the grey water footprint, because of that virtual number that you're adding onto the side, always dominates this, depending on how you are setting the system up, but it almost always dominates. Ways to get this better, or so that you don't have as big a grey water footprint. Obviously, you can see by the maths. Let's take out the concentration. Let's reduce the amount of pollutant that we are sending out. So let's have a wastewater recycle here. Let's treat the water. Let's take out some of the contaminant, or let's not put this into a nice clean dam. Let's take this and put it into a wastewater treatment system. Okay, so we're not putting it into the environment. We're putting it into something that is already polluted that then gets cleaned up again. Okay, so you might clean this up in your own site, but then you'd send it off to a municipal treatment site or some other industrial site, and then they'd do it again. So you get a better score that way as well. I'm going to take another slight detour and go through why is actually measuring water like this important. So we're talking about this grey water footprint, this blue, green, all of this, but why exactly is this even important? And some of the stuff that's important here is also going to be important for the life cycle assessment and maybe a little bit for the carbon footprint as well. So why is this important? So let's go back and let's start with the story. If we go onto Google Earth, so you will notice that this says 2009. So I've done this purposely for 2009. I've left the data from 2009. I actually think it says 2010 somewhere. So this was actually loaded on 2010. The 2009, this is a 2009 map though. On that map from 2009, you can look up Kazakhstan, and on the bottom here, I haven't got it written, but this will be Uzbekistan on the bottom here. On their border, there is something called the Aral Sea. The Aral Sea, according to Google Earth, follows this line here, this yellow line where I'm now highlighting all the way around here. This is a sea. So from this diagram, you can't get really a sense of how big it really is, but you can get a sense of where's the water. So it's an inland sea, and when it's called a sea, you'd imagine it to be big. But a sense of how much water there is. There's only this little bit of blue here. There's some blue over the side here, and there's some to the top here. I've left this as 2009 because I'm going to compare 1975 to 2010. If you look at other maps from 2010, 11, 12, you'll sometimes see that there's a little bit more water in this little opening here. Sometimes there's even less water than this. That is simply due to whenever Google took their latest little snapshot, there might have been a slight bit of rainfall or less rainfall, but it never gets to more. This is pretty much the average of what it looks like. What I'm now going to do for the next few slides is just start zooming in. So I'm going to start by zooming in to the topmost part of one of the water areas, but also to the nearest or the biggest nearest town. So that is Aralsk, and I'm sure I'm getting the pronunciation of everything wrong here, in Kazakhstan. So that is one of the major towns here. So just to give a sense, now we're getting a sense of the scale. So that's the nearest town, and this used to be a harbor in here. If you look very carefully there, you can see there's actually a little bit of water left. However, this is a harbor town, so this was at the sea. It is now, on my rough Google Maps distance calculator, it's 20 kilometers away from the water. We're now going to zoom in again. So remember, this is 20 kilometers away from the water. That's how far it is. But how big was the sea, and what exactly was the scale of the operations? So just going in again, there's that little bit of water that I showed you earlier. We're going to go in again. So there's this little bit of water that we now see in here. This was the old harbor. So I'm not quite sure where exactly the harbor went to, but this is the scale of the harbor. How big was that? Well, if you have a look there, I've highlighted or I've circled 3 ships or boats. I don't know what those ones are. And if you look around, you can see there's another one there. I think there's 1, 2, 3. There's another one, a couple there. They're all over the place. So there are all sorts that are lying around. I'm going to zoom in again. Not necessarily on that one, though. I think I'm zooming in on this top one here. We zoom in. No, it's a totally different one. Sorry. We zoom in again, and here is now one of these ships or boats that's on here. And by my mind, this should be longer than the measurement I've given you. That's 51 meters, so that's not a small boat. That's probably ship. By South African standards, that's a big boat. That's a ship. So this is probably a little bit longer. It could even be 60 meters along here. So there's 1, there's 2. There are another 2 here that are abandoned in this area here. So in the scale of how important this was a fairly important sea. It had ships that were on it that were 50 meters and longer, And there were lots of them. There weren't just one or two of them. So firstly, point to highlight is that this sea was important enough to have, even though it looks like a lake or a dam to us, it was important enough that it had lots of these big ships. So they were obviously transporting backwards and forwards, doing various different things around the different areas. The other thing to notice is that these ships are now abandoned. There's nothing. Why didn't they move these ships to another port? Why did they just wait for the water? Why didn't they move these somewhere else? Or why didn't they salvage it? What was the point in leaving this? The reason is that this water subsided so quickly. It subsided so quickly that these ships, it was easier to just leave them here than find a new home for them, or how do you do them? This is a landlocked type of sea anyway. If you go onto Google, and for those of you that don't know, Google Earth rather, and on the left-hand side there are these different layers. One of these layers is Panoramio photos. So if I tick Panoramio photos, it gives that little icon there, and you'll see some of my previous slides. You'll also see there these little dots, these little things here. They're all over the place. If you hover over them, and particularly in this area, you'll see that there's one that's miles away. What's this? 7 kilometers from the sea. There's a ship that's just been abandoned. It just got left to disintegrate. Nobody's even gone to steal the metal or anything. There's so many of these ships that are just lying in the middle of nowhere. So this was clearly a big problem, that something happened here, that all of this happened. The other pictures, here's 1, 2, 3, 4, 5, 6 ships. There's a dredger that tried to salvage these, but obviously didn't succeed. So it was a problem both for the ships, the industry, but it was also a problem for animals. Animals also managed to, were unfortunately suffered due to this big event. So as I say, and I'm sorry I've forgotten the date on here, there is the 1975 diagram on the left. That's where the sea was. And now in 2010, and a similar time frame, you can go and have a look now. There's all this space here where there's no water. So why on earth why am I actually even telling you this? So let's just go back and sort of what exactly is all of this about? So what this is, as I've already said, is this is on the border of Kazakhstan and Uzbekistan. And what it was that it was formerly one of the 4 largest lakes in the world. What exactly happened, and why am I highlighting this to you? What happened was that there was, in the 1940s, or maybe probably earlier, there was a plan called the Great Plan for Transformation of Nature. And the idea was to have a whole system of canals. There's a whole lot of free water, or free, I suppose. Is it free? Isn't it free? There's this water that's available. So let's use a system of canals and let us start building canals to supply the farmers in the local areas. So this construction started roughly in the 1940s, and it was a system of many canals. So it was a quick, fast, we've got lots of water, let's not worry about it. It doesn't matter that they're poorly built. If there are leaks, it doesn't matter. We don't need to cover it. Why would we cover it? If there's evaporation, so what? There's so much water, it's not a problem. So it was, and I don't know how to pronounce that word, I'm not even going to try. The largest, so that was from this canal, the largest in Central Africa, 30 to 75% of all the water went to waste. Okay, so a lot of that water, 30 to 75% of the water went to waste. The thinking in those days was that, well, look at the size of the sea, 30 to 75% going to waste. Do we really care? There's so much water. So what? Only 12% of the irrigation canals today is waterproofed. So even so further back, it was probably even less. Was any of it even waterproofed? Was it just a ditch in the, I don't know what it was. Was it a ditch in the ground? What was it? We're talking here, and this is information from Wikipedia. You can go and see that. You can go and Google it. You can see it. Oh, we'll go and check on Wikipedia. You can see it as well. I'm not even sure if any of it was even covered to prevent the evaporation. Why did they do this? I already said irrigation. So it was mainly to grow rice, melons, cereal, and cotton. So cotton is actually the big one here. So all of this was part of the Soviets' plan on white gold. So cotton in those days, even today, I suppose, is valuable. As a crop, cotton is very valuable, particularly for the Soviets, in that it could become a major export product for them. They could build their economy through the use of cotton and cotton farming. So around the Aral Sea, there was a lot of cotton farming, this white gold. And the idea was that the Soviet Union in those days would become the world's major cotton producing area. So they did manage to do that. So even today, Uzbekistan is one of the world's largest exporters of cotton. So from that sense, they were very successful. Their industries grew. There was enough cotton for the world. They could become a major hub for cotton. The problem with this was that between 1960, or sorry, that by 1960, between 20 and 60 cubic kilometers were removed annually from inflow. That is to the sea. And I need to stop you there. I can't get my brain around that number, that 20 cubic kilometers. If I was in front of you, we'd be sort of trying to imagine this with my fingers outstretched. I can do 1 centimeter. I know what 1 centimeter cubed is. 1 meter, I think I can imagine that. As soon as you talk about 1 cubic kilometer, so that is 1 kilometer long, 1 kilometer wide, and 1 kilometer high. 1 kilometer high is a ridiculous height. Times that 1 by 1 by 1 kilometer by 60. That's how much water was removed annually. So in 1 year, 60 cubic meters was being removed in the 1960s. So that number of between 1960 and 1920, the amount of water taken out from the rivers was doubled. Okay. What was good, as we said, is that the cotton production also doubled as well. So from a commercial point of view, it was a highly successful operation. What we need to now do is take a step back and go and look at water intensity. So if we're looking, and I used to have this as a flick 1 by 1, but let's go through this one line at a time. 1 kilogram of cotton is said to use 8,859 liters of water. So how on earth do you use that much water? This is all because of the water footprint that we were talking about earlier. So some of it is green water, blue water, gray water. And remember, this is water that's lost. So if you're taking water from a dam or a lake like we're doing from this Aral Sea, you water your crops, you are going to lose a lot of water through evaporation. Cotton is not a very water-intense product, final product. Our t-shirts that we're wearing aren't wet, so it's not like an apple, so not much is going to be incorporated. But we're also going to get pollutant. We're probably going to have fertilizer on the water. So as soon as, or on the crops rather, so as soon as we water the crops, because there's fertilizer in it, technically by the water footprint method, we can't claim that that water returns to its original source because it's now polluted. So cotton is fairly water intense. It's 8,859 liters of water per kilogram of cotton. Uzbekistan and Kazakhstan were producing 4.5 and 2 million bales per annum respectively. The mass of cotton is 1.5 million tons. So if we do a mass balance on that, just from the cotton, that is an equivalent direct water use of 13 cubic kilometers of water per annum. So that's purely on a mass balance, doing some ratio calculations on that. We've already said that there were up to 75% losses. So that means with loss of 75%, we're now up to 53 cubic kilometers per annum. So that's where that number that we got earlier of 60 can come from. That's how we knew that number. As a comparative scenario, water losses of 75% give us 53 cubic meters. In South Africa, our total water storage, so every single dam in the country, and this is I need to just double check this number, but I know it was right in about 2010, 2012, the water storage in our country was only 31 cubic kilometers. With all the rain and all of that and the usage that we have, we typically have a recharge, or from rain rather, we have a recharge of 46 cubic kilometers per annum. So we don't even have enough water in the whole country to supply the water for the cotton industry in Uzbekistan and Kazakhstan, mainly due to all of these losses. Okay, so why do we need to worry about water and water losses? Because obviously if you start on, this is the extreme, we are going to end up with seas, lakes that just simply disappear. As a comparison, I've got some numbers on the right-hand side here. So we said cotton. Have I got cotton on here? Well, we have cotton on the left. So cotton, we said 1 kilogram of cotton was 8,800. The comparative for bananas, 859. That's much lower. Tea is then 9,000, 10,000. So these are much lower than, sorry, there's the cotton again. Missed it earlier. So 8,859 for cotton. Olive oil is fairly high as well, as is coffee. We'll jump down to the bottom here. All of these, though, are a lot lower typically than meat. So often you'll see that vegetarians are saying that you see it's water intensive. So here you see the numbers. For chicken, lamb, and pork, it's 6,000, 3,000 ballpark numbers. Beef is 15,000. So you'll say, well, 15,000 compared to this 21,000 for olive oil, it's not really that much difference. I'm pretty sure there are people who will eat half a kilogram of beef in one sitting. None of those people will use half a liter of olive oil on their salad. So typically you'll use much less olive oil than eat meat. So from these just some examples. So this, as I said, Hoekstra comes up quite often. So Hoekstra and Champagne 2008. We've got chocolate, which is 2,400. Sorry, what's this? Sugar, 1,500. Tomatoes, 180. Wine, 120 for a glass of water. So just please note some of these. Check the units that we're looking at for each of these. That's for per glass of water. Wine. One hamburger, 2,400 liters. Leather, 16,600 for 1 kilogram of leather. So it's not for a shoe. Just note that it's for a kilogram of leather. One sheet of paper needs 10 liters of water. That's probably due to some of the water treatment systems. Coffee is 140 liters of water. So I want to stop here and just ask some questions. So this is now where I'm linking back up to life cycle assessment. I tell you that, or this study, I don't tell you, Hoekstra and Chopin tell us in 2008 that for 1 cup of coffee, we are using 140 liters of water. I have a lot of questions for this. So what exactly is this cup of coffee? And I'll put a link to a paper that I've got the comparison of this. So I have written a journal paper on this. What exactly is this cup of coffee? Is it instant coffee, or is it filter coffee? Is it recoffee? Is it Jacobs? How big is your cup of coffee? Is it 200 mils, or is it one of those Starbucks things that you can buy as souvenirs that is half a liter or 3/4 of a liter almost? Is that just the coffee? I don't see milk in here. I don't see sugar. So is that just coffee? What is that? So this is going to be one of the problems with LCA as well. So not just water footprinting. How have we defined everything here to get the 140 liters? This is a reference from Hoekstra and Chopin. I also have another reference. And unfortunately, I don't have this reference in front of me. I'll go and find the paper and share it with you later. But here's another reference who says that for 1 cup of coffee, we have 208 liters per cup. So this time they've at least given us a little bit more information that says that there is 2.4 liters from the lid. There is some from the cup. I don't know what happened to the numbers for energy and the wrapper. They seem to have disappeared in this diagram. We can maybe do it by the mass balance. There's only 0.8 liters for water. There's some for sugar, there's some for milk, and here again they've given us the coffee number. So this time they said it's 142. So maybe with rounding errors, 142, 140, it's fairly similar. So nobody's probably going to argue between the difference here. But this sort of diagram gives us a little bit more understanding or a bit more comfort to realize that 208 liters per cup is for everything versus 140. We now know that that was just for the coffee, no sugar, no milk, no anything else. The last point to note on the cotton consumption, the water footprint for cotton consumption as we've been looking at, is that what we effectively have is that there's a virtual trade of water in this this Asian area because of the demand for cotton in Europe. So Europe isn't asking for water, they're asking for cotton, but as you can see, because of this demand for cotton, they are effectively using the water. The water might not necessarily be all traveling to this area, but the areas where it's coming from have water. Water is being used, so they're affected by this because of this trade. So this is the one for blue water. The same way we can have it for green. You see there's some trade because of the green water, and the same thing on a lesser scale for the gray water for cotton. In the same way, South Africa, we're a water scarce country, so we can also have this see a map like this for the virtual trade of water, particularly through our things like grapes or apples, where we have this down in the Western Cape, the series areas, water would be effectively traded up to Europe. In our instance, water is embodied, it's part of the apple, so water is literally leaving our shores up to Europe. If we look at the legislation now, so what exactly is it that is required to do a life cycle assessment or a carbon or a water footprint? So there are 4 standards, or the ISO standards, so that's the International Standards Organization, ISO. So there's the ISO 14040, which looks at the LCA, as well as ISO 14044, which looks at the requirements and guidelines for LCA. So the first one is principles and framework, the next one is requirements and guidelines. We then have a ISO 14046 standards for water footprinting, and ISO 14064 for greenhouse gas management and related activities, which is the carbon footprint. While the ISO standards are guidelines, in South Africa we have something legislated. So we have the National Environmental Management Waste Act 59 of 2008, and in that there is the Extended Producer Responsibility Section 18.2, and under that F we have the Minister may in a notice under subsection 1 specify that the producer of a product or class of products identified must carry out a life cycle assessment. So while I've not come across any companies that to date seem to have been required to do this, or if they have been required to do this, it's not been public knowledge. There is now an extension of this, and at the end of this year, that's the end of 2021, there is the extended producer responsibility legislation coming in that says that everyone is going to have to do some form of life cycle assessment. So while the extended producer responsibility legislation goes much further than that and gives other requirements that are needed, life cycle assessment is going to be one of those, or one of the requirements for that legislation. So what I want to do now, so in the last section of slides, is to actually go through what exactly is a life cycle assessment. So this is following the ISO, so we can see down at the bottom here, the ISO 14040-2006 standard. So in the standard, it sets out how a life cycle assessment should be done. So if you want to claim it as an ISO certified standard, this is how you need to do it. So first of all, they set up the structure or the life cycle assessment framework such that it has these 4 different sections. The first one is goal and scope definition. There is an inventory analysis as the second step. The third one is impact assessment. And the final, or the one that runs across all of them, is the interpretation. So you'll notice that these arrows go backwards and forwards, up and down, left and right. So all this means is that even though we're going top to bottom on the left-hand side, it's saying that if you find something wrong, don't sit there and just carry on going all the way to the bottom. Go back up a step, check what you're doing, go back down a step, check again, go down, check. The check is this interpretation. So how do you interpret what exactly are you doing? At each step, what are you doing? Define the goal, check, go back, are you happy? Up and down. So it's a very iterative, round in the circle type approach. The way I will present it is how you are actually doing it is from the top to the bottom here, but just as a reminder for this interpretation, you're checking at each step along the way. The first block on the top left was the goal definition and the scope. So basically what this says is what exactly are you looking at? Is it 1 kilogram of biodiesel? Is it 1 liter? Is it 1,000 liters? What exactly are you going to include in your study? Are you including cradle to grave, which you should be including? Is there something that you're not going to include? And what is the reason for not including that? So it might be you can't get the information, or it's some little aspect of the project that is so small you can comfortably say that it's not going to impact your study. So is it just a weakness, strength and weakness analysis? Is it a product improvement assessment? Comparison, eco-labeling? This is all set up in the goal definition and scope. So basically what it is it's the aim. The most important one here for us, though, is what is the functional unit. The functional unit can be very specific and often is. So it can be something, so some people might say that it's something like driving a car. So it's not going to be driving a car, it's going to be as specific as driving a 4-door BMW 320i 2019 model with 4 people in it from Johannesburg to Cape Town. So that's how specific the functional unit can get. Important reasons for having this is so that we know that we're on a level playing field if we at any stage we want to compare something. So when we say 1 liter of apple juice, it's not 1 liter of apple juice, it's 1 liter of apple juice produced in Cape Town using this method, this agricultural method in 2019, average data over a single year, over 3 years, over 5 years. So when you put it on the shelf in your Woolworths equivalent type shopping center, and you pick up that apple juice versus a different apple juice, you can see that the one is 2019 data, the other is 2018 data. So which one is more relevant? That sort of thing. Obviously, it needs to be clear and accurate of the description, which is, I think that goes without saying, yes. That can then limit the alternatives. So because we're going up, down, left, right on the original diagram, it can be a bad thing. So if we get somewhere down to the bottom, we realize, hang on, why have we got 4 people in our BMW? Why don't we have 3 people in our BMW? Do we have to start all the way at the beginning? So that could be a bad thing if you limit yourself too quickly. But it could also be good because now we know we've got 4 people in the car, not 3 people in the car. Okay. At this step, there's also another type of decision that we need to make. It's whether the LCA is going to be attributional, and that is as is. So whatever we do, we're not going to worry about the changes that we are going to make because of our process. 99% of LCAs are attributional. There is also a consequential LCA, which means that if we build some massive facility in the middle of Joburg, what are the consequences to everyone around that going to be? We now need to have more electricity from Eskom. We're going to have to change the roads. We're going to have to get a new Sasol built because we're using so much petrol. We need new petrol. So the consequential is what would happen around us as well. So there are obviously going to be changes to everything around us. It's much more complicated to do that, so we're not going to worry about the consequential LCA for this course. These things here I think are fairly obvious, and it's things that I've already said. What do you want to know? Who's doing the study? Why are you doing it? What's the study? What's the scope? So that is all part of an aim, which would fall under the goal definition and scope. The next box was the inventory analysis. The inventory analysis is effectively a mass and energy balance process, or mass and energy balance exercise rather, over the entire process. So my original blue box diagram, where we had the box that was then extended back and back and back, that is what you're going to do here. So from the goal and scope, you've decided what you're going to do and what you're going to include or not. This step now needs to look at every single input and every single mass and energy balance all the way back. This step is where 99% of the work happens. So for your own site, you're obviously going to know, or you hopefully know, you can go and figure out what the mass balance is. If you now go and ask your suppliers what their mass balance is, it's either going to take you a long time to convince them to do this, or they're not going to give it to you, or yeah, it's going to be work. Because of this, there are databases available. So there is specialized software that you can download, and you can go and pull out the modules that you need. So you literally put together a chain, or they call it a network rather, put together a network and interconnect everything for electricity, all your chemicals, raw products, as is available in that database. So sometimes things are available, sometimes not. So the current database, the state-of-the-art database, is sitting on about 90,000 modules. Those are very specific for certain countries or certain products. In South Africa, we're still building up that database. So I think we're currently sitting on about 20 items. So if you had to do an LCA for South Africa, we would have things like electricity and I think some of the fuels, gold, platinum, those are in there as well because we are big into mining and other countries wanted those, so South Africa produced those for them. And then there are a couple of other random things in agriculture and the like. Okay, so we said already these inputs that we need for mass and energy balance. We also need the environmental emissions, so we want all of the emissions as well, just to highlight that there. So I think I've already said some of the things that are needed here, so maybe I don't need to spend too much time. So the first step of this would be constructing that process flow sheet. So we want to have the flow sheet from the beginning all the way at raw materials on the left-hand side, or energy from the environment, with the ultimate ending being the product, as we had on that original diagram. Some of the problems associated here may be that we have co-products. There are ways to allocate the environmental burden across the products, which I'm not going to worry about, or how we allocate things. We're not going to worry about that here. Then obviously we also want wastes, the solid, liquid, and gas. So just as an example, an inventory analysis example, what am I talking about on some of this? So let's just say that the manufacturer of a low-fat margarine, to manufacture a low-fat margarine, we need various steps. So obviously we're going to grow the crops, convert the crops. There's packaging, transport, consumption, disposal, and recycling for just making low-fat margarine. So what that means is that we're going to, for the inventory analysis, we need to know what is the process flow sheet. So this is all the way from, so you've got the plant cultivation on the top. We have the plants being cultivated. They make margarine. At the bottom, we have mineral oil to make a plastic, which then gets a packaging. The packaging is used on the margarine. We eat the margarine, and then we dispose of the packaging at the end. So you're going to have to know what is this flow sheet, and this is possibly even a little bit simplistic. From that, we now need to figure out what's the mass and energy balance, what chemicals, electricity, there's going to be transport, water, fertilizer, and the like across here. So it's the flow sheet development and then doing the mass and energy balance for all of these items across all the chain for whatever our functional unit is coming out at the end. So I've already spoken about a database that is actually available to do this. And the way that it's described is in foreground versus background processes. So the foreground process is everything that you need to collect yourself, whereas background data is something that you can get from a database. So typically, let's just look at an example here. So typically, if we're making a biodiesel, well, not typically, let's just say we're making a biodiesel as a product. To make biodiesel, we don't tell our competitors what we're using. We just tell them it's a secret chemical A, secret chemical B. It might not be that secretive, but We don't want to tell our competitors what it is. So the foreground process is everything that we don't know. So we don't know, or sorry, that's not available in the database already. So biodiesel is not in the database, so we would have to go and produce the flow sheet and get the mass and energy balance. Secret chemical A is, I'm just putting it as a secret chemical here because it's something that's not known. These two, we would have to do the mass and energy balances as well. Everything else that's an input here would be simple things like electricity, water, and transport. Those would probably be in the database. So those would be referred to as background processes. So it's obviously important when we're doing the mass balance, or sorry, the flow sheeting, that we need to define the boundary properly. So once these are defined, we might want to refine them. Sorry, once we've defined them and we try and get the mass and energy balance, you might notice that you can't get certain things that are very far to the left of the flow sheet. It is possible to then more carefully define the system, so we can just cut things out, but every time you cut something out, you need to specify why you're cutting it out or you're excluding it. This is the whole reason, or one of the reasons rather, why we say LCA is iterative. So you would now say, okay, I can't find this information. Let's go back up the chain and go back to the goal and scope definition, reword the goal and scope definition to say I will not be including chemical A, chemical B, whatever it might be, or some part, because I can't find the data, not because I can't find the data, but because it is such a small contributor to this, I assume that it's not going to contribute too largely, so I'm redefining the boundary. Obviously, that system boundary can be influenced by the goal of the study, and the big problem here is that subtle changes can have big influence on the final LCA. So if you are going to redefine the boundary in the top step, it could have a big change on the actual outcome, so you need to be careful on that step there. So the other way that we could look at the inventory analysis is in this example here. So it's not always going to be the full cradle to grave, as I said before, but it could be from a gate to gate or a grave to, sorry, gate, cradle to gate or gate to gate. So let's just look at this example. So for safety reasons, a modification in a beer brewing facility is going to ask that for the packaging process, so only the packaging process is going to be changed, and that packaging is going to now use natural gas instead of electricity. So we're only looking at the packaging part of this. We're not going to look at the entire process. With that, there's been a request to look at the LCA. What is the change in the LCA scores if we had to do that? So when we look at I'm trying to click it right. When we look at the two flow sheets, on the left we have the original flow sheet, and on the right we have the new one. So on the left, we have electricity both at the brew house, and we're using electricity in the packaging. Whereas on the right, we're only using natural gas. For this example, I'm just going to assume because we're changing from electricity to natural gas, we might change the plastic or something. Maybe there's some other change that we'll just look at here. Chemical A, chemical B, the plastic packaging, the wood, the paper, plastic, or the cardboard might change as well. So if we have to do an LCA of this, what we would do is we would take the boundary to be the entire system. So we'd say the LCA on the original plant for 1 liter of beer would be something. Whereas on the right-hand side, the LCA of everything would be something else for 1 liter of beer. The question, though, was what is the difference between the two? So we would take the left-hand side, the right-hand side, subtract the two of them, and then work out what the LCA is. So that would be the proper way to do it by the ISO standards. However, we are not really interested in how much it costs, environmental cost of 1 liter of beer. We only want the difference. So if we only want the difference, we're only going to look at that portion of the system that is different. So the difference would be in the packaging on both systems, and then obviously on the left-hand side, the original plant, there's only a fraction of the electricity that's now coming in. So this is why we would do a gate-to-gate LCA, is because we've got the LCA just for that portion in the red square plus the electricity. We do the same thing for option B, and then when we subtract the two, we know what the difference is. If we have to do it for everything else, all we're doing is wasting our time doing the LCA for these two sections here, as well as the transport, when it's exactly the same on the right-hand side, and it basically cancels itself out anyway. So once you've got that flow sheet and you've got the inventory, we need to actually start processing the data. So you're going to have tons and tons of mass balances, values that are coming in, values that are going out. But what we actually want is to know how much of everything do we use per functional unit. So if our life cycle assessment is for 1 kilogram of product, we need to know how much raw material do we need to make 1 kilogram. So this is going to basically involve a whole lot of scaling factors so that all the values are related or relative to that functional unit. So because at this step, we call it an inventory table. So that's where the inventory analysis, we now put that into a table. So typically in Excel or something like that, down the left-hand side, we would have thousands and thousands of chemicals. And on the right, we would have all of their mass values. Typically, all of these are now in mass values. So even if we had energy, because we said it's going all the way back to the raw materials, electricity is going to start from coal, from biomass, from some other thing that we've burnt, or something like that. Even if it's nuclear energy has a something to it, has a mass or a nuclear value. Wind energy, the same thing, or hydro. So we're not necessarily going to take into account the wind or the water in making the energy because that's the renewable part, but we did have to make the materials in the first place. So what did it actually take to construct the wind turbine or construct the hydroelectric dam? In many cases, we actually don't include construction in the LCA. The reason for that is that when you construct something, if we look, let's start again. If we are looking at 1 kilogram of biodiesel, for example, and we have built a plant, that plant is expected to last for 40 years, for 60 years, making tens of thousands of liters of biodiesel every year. If our functional unit is 1 liter of biodiesel, the amount of concrete that went into that plant per liter of biodiesel is going to be so small that we often ignore it. So construction phase is often left out of LCA calculations because it becomes so small when you do this scaling factor that we're talking about here. That step there, as I said, this step for the inventory analysis is where it takes 99% of the time. However, not all the impacts, all the environmental issues are necessarily accounted for in this inventory table. So I've already said water is sometimes not always properly accounted for. So in particular, rain or evaporation might not necessarily come out. And then it's often common that we have different water purities. So you've got, if you're using river water, for example, for cooling, it doesn't really matter what the purity is on day 1 versus day 2. So sometimes that might be just left out. This set here that I'm talking about is not always properly accounted for, is part of your original goal and scope. Are we including it? How are we including it? There are some other things, and the one example I can think of is erosion during mining operations or just the digging in the ground. Sometimes it is accounted for. There is an option for land change, which they call it, but then erosion and things like that may not always be accounted for. I mentioned before that geography is not necessarily taken into account, or it might be taken into account. It depends on how you do it. So geography is taken into account if you are looking at the database, so the original database of the LCA database rather, it might say that you are using the electricity module from South Africa. So that is definitely taking geography into account, whether you choose South Africa or Australia or America for whatever inventory data you are taking. But there's certain things that it doesn't take into account. So we've chosen the South African module. But if you've built your oil refinery in Sandton versus Sasolburg, and the only reason I chose those two is because they both start with S. So Sandton, if we had to build an oil refinery in Sandton, it's a well built up area. It's got quite a bit of commercial and real estate there. People would be a lot more upset if it was Sandton or that sort of area versus Sasolburg, where originally it was out in the middle of nowhere. There was no one around it. So those sort of geographical things might not necessarily come out properly. I've said it before, this inventory table can literally account for thousands and thousands of numbers. When you use the LCA software in the database, there are people who have done this over many, many things, and they measure mercury into the minutest detail and things like that. So you will see thousands and thousands of numbers. The next step is going to be processing this data. So we want to transform all this data into some sort of convenient form. So if you're lucky, you've got the software that I talk about. If you're not that lucky and you have to do this by hand, you're effectively doing all of this in Excel. So what the software does is it is actually basically just Excel. So it's not that fancy a software tool. It just lays it out very nicely. So we would want to calculate the specific amounts of components used per functional unit, and we would want to add them all up. So there may be instances where something is used in a process more than once. So it's used for electricity, it's used for transport, so things like gas or coal. So you'd want to make sure that they're added up across all of that so that we don't, just so that we can trim the numbers down. The next step is going to be impact assessment. So the impact assessment is the third step on that original diagram from ISO. The previous step of inventory analysis is based in Excel, and that is all, like I said, 99% of your work. The impact assessment is now either done in the software, or you pull the information off the internet on how to process your inventory analysis into impact assessment. So you're not really doing any clever maths or anything like that, you're just manipulating the data now. So what we're doing, as I say, is taking that inventory table and analyzing it. We want to take those thousands and thousands of mass data points, and we want to transform them into some meaningful environmental number. To do that, we are going to do this in 3 steps. Firstly, classification. Then we're going to characterize and normalize. And lastly, we are going to do an evaluation. The classification now depends on the method that you want to choose. So there are various different people around the world. There are groups in America, there are groups in Europe, there's some in Japan, I think there are, that have all come up with their own methods on how to do this. Ultimately, you're coming up with the same type of final answer, but the exact maths behind it is going to be different. Because they've come up with different types of methods, they've also categorized or classified differently. What happens is that each of these thousands of inventory table data points are going to be classified according to a problem. So these problems could be something like acidification or acid rain, land use change, as I mentioned earlier, water use, greenhouse gas issues, eutrophication, they're various ones. So the global warming, the greenhouse gas issue, depending on the method that's being used here, is effectively equivalent to the carbon footprint that I mentioned before. For it to be a carbon footprint, you have to use the method developed by the IPCC, International Panel on Climate Change, So they have decided how you need to take this step forward, as we're going to be doing now. Okay. It's important to note that certain inputs or outputs from the inventory table can contribute to more than one environmental problem. So sulfur or nitrous oxide or something like that may lead to photochemical oxidation. It may lead to smog, to ozone depletion, to global warming, to various other things. And you'll see what I mean in a moment. So I've already mentioned that several categories exist. But if we look at some of the examples, so these aren't all of them. There's resource depletion, energy depletion, global warming. So as I said, global warming in an LCA context is effectively a carbon footprint if you do it by the IPCC method that we're going to do on the next slide. Photochemical oxidation, acidification, toxicity, ecotoxicity, and eutrophication. This is a very short list. There are others that go on much longer. So you might look at marine toxicity, aquatic toxicity, there's human, there might be animals. I'm trying to think what else I'm missing off here. Land use change, I already said there's a land use change issue, and various other things. I see water is also the one that's missing. So sometimes there are some methods from the water use in LCA group that looks at the absolute or the water scarcity index as well. So what exactly is this classification? So what I'm just going to do for these slides where you see the person with a pen on here is we're looking at a large inventory table that's been presented. How are you going to manipulate the data in order to produce a final LCA? So first step is the classification. So what that means is we had this inventory table. So from our mass and energy balance and the full process flow diagram, we are going to have, this is our thousands and thousands of chemicals. And I'm not going to present all of them, but this is just an example of how we do it. Depending on the method and whose method you're talking about, so there's recipe, there's the IPCC, there's the US EPA, there are people in Japan that do it, they all now come up with this classification scheme. So it doesn't matter which one it is, this is just an example. We have global warming, acidification, and eutrophication. In this classification step, they have now done years and years of chemistry, human health studies, and various other things that have now determined that global warming is, the chemicals listed here lead to global warming. So carbon dioxide, carbon monoxide, methane, SF6, and a couple of others all lead to global warming. In the same way, these gases here contribute to acidification. These ones contribute to nitrification or eutrophication, depending on where you see it. You will see here, and this is the example I want to show you, that there is a NOx that contributes to nitrification, but it may also contribute to acidification. So you may see some chemicals popping up more than once in the different classifications. The next part is the characterization. We want to characterize these. So the characterization and the normalization, so each of these chemicals in that given, each of the chemicals in the characterization or in the impact assessment category is going to contribute a different percent or a different weighting to the total score. So as the very good example of carbon footprinting and global warming potential, 1 carbon dioxide is equal to 1 carbon dioxide. If we had to release a carbon monoxide chemical, there's been a lot of chemistry done, and how does a carbon monoxide chemical relate to a carbon dioxide? So instead of having all of these different chemicals, we convert by a weighting all the chemicals to a single unit. In global warming, that's going to be the CO2 equivalent. So 1 CO is going to have a weighting that will make it equivalent to a CO2. The same thing for methane and all the other chemicals. These characterizations can take location and the fate of the chemicals into account. So obviously a carbon monoxide is not going to stay as a carbon monoxide forever. It's going to react with another oxygen at some point, and it will eventually become a carbon dioxide. So it's those sort of things that are looked at in determining these weighting factors. So often these values are meaningless in isolation. So that's why we look at them in terms of a comparison. So in LCA, we often want to compare things. So you may have seen on some, if you've ever flown somewhere before, some of the airplanes offer you do you want to buy your carbon tax? Do you want to pay your carbon tax or something to that effect? And they'll say that from Cape Town to Johannesburg or vice versa, you use there are a certain number of tons of CO2 that you've emitted. To most of us, that doesn't mean much. So if we are talking about Sasol, and Sasol says they emit 3,000 tons, that means very little to you and me, I think. I don't know. What is more meaningful is if I can compare, if Sasol emits this much, how much does Engen emit, or how much does Eskom emit? If I can compare apples to apples, it makes it a lot easier. So this is where normalization also comes into account. So normalization is going to, I've jumped a step here now, sorry. So normalization is going to look at how do you compare to everyone else. And we'll come back to that on the slide after this, actually, I think. The characterization and normalization, and I think the slide I've been talking to it already, you need to decide which issues may be important. I'm just trying to see what I haven't mentioned on the slide already. I'm talking without really reading the slides because I know I've been asked not to read the slides. So what we're going to do at the end is we're going to convert all of the CO to CO2, the methane to CO2, everything in that category to CO2. We then add all the equivalents together in each of the categories, and we're going to get a single value for each impact category. At the end, what we're ultimately aiming for is roughly 10 to 20 numbers from that original list of thousands. So thousands and thousands of numbers are meaningless, but 10 numbers, at least we've now got something to compare with other people. So coming back to the normalization, sorry, I thought this was the next slide after I mentioned it previously. So if I know that Sasol or whoever it might be contributes a certain amount of CO2 equivalents per year, I can then look at what is the total global CO2 emissions. So if I have a process that's only emitting 1 ton of pollutant, again, I don't know whether 1 ton is good or bad, but then if I can find that the global number is 1 million tons, how does 1 ton compare to 1 million tons? What the normalization data then does is it looks at 1 ton out of 1 million tons per year. So it effectively comes down to it's 1 millionth of a year is how much I'm producing, or 10 to the negative 6 years, or I'm only contributing 32 seconds out of the year. So normalization is the process of looking at my data, my company's data versus the world total. And that way I've got a better understanding of what the differences are. Coming back to this in terms of this diagram then. So we've already classified and we've said CO2, CH4, SO, and SO4 for classification. The next thing is the characterization we said. So here we can see what we are actually doing. So 1 CO2 is obviously 1 CO2. 1 CH4 by this method is the equivalent of having 23 carbon dioxides. 1 carbon monoxide is the equivalent of 1.53. The big one here is 1 SF6 is equal to 22,200 CO2s. So we don't want to be emitting SF6. So luckily for us, it is a rather rare chemical, so it's not going to be emitted too much. LCA now is effectively taken that inventory data, that massive mass balance, assigned it to each of these classifications. Each classification grouping has weighted each of the chemicals. We convert the original masses by that weighting factor. We add them all up and we get a single number. So we can now say that our process, our 1 kilogram of product, now has an LCA of whatever that sum of CO2 equivalents is. So it might be 3 CO2 equivalent, 300, 3,000, we don't know. As I say, on isolation, that means nothing, but at least we can now compare. In the same way, we can do it for all the other categories. So I haven't put the weighting factors here. Acidification is actually related to SO2. Nitrification is related to the NOx. So if I look up the different methods, and these are all online, I can see 1 SO2 is equivalent to 1 SO2. 1 NOx is equal to how many SO2s? 1 ammonia is equal to how many that? Again, we sum them all up to get the characterization and then the totals, which these results would be our final LCA number. The last step here is the valuation. So valuation is not actually part of the ISO standards, and this is, I should probably in future take the slide out. So valuation now looks at what would happen if we take all of those numbers and make them into one. So it's the final step of the quantification, and we're going to convert all of the characterization values into a single value. Again, each of the characterization values are given a weighting, and all of those values added to give a single value. So your final LCA score used through valuation is, as I say, it's going to be 1, 3, 5, 300, 3,000. I don't know what it's going to be, per kilogram, per whatever you've got. It is still used, but not recommended in terms of the ISO regulations. So that's why I say maybe I shouldn't actually put these in future. So just looking at this from a diagram, what we'd take again is we'd weight all of these and we'd put them into a single environmental score. For future reference, just because I say this is now becoming the outdated way of doing it, the more recent way of doing this is rather to call this middle step a midpoint indicator. So a midpoint indicator is in terms of masses. So we've still got, or an equivalent mass. So it's still a CO2 equivalent. It's going to be in kilograms. Equivalent SO2 kilograms. These are all in masses. These are called midpoint indicators. To you and me, as I've already said, what does it mean to actually have 1,000 kilograms of CO2 equivalent? It doesn't really mean anything to me unless we compare. People in public health, so this is let's go back. This is an engineering exercise. People in public health have now come across this and seen, or they've come across this long ago, but they've looked at this and said this doesn't mean anything to them either. But being doctors and being in the Public Health Institute, they can look at this and say, okay, well, if I'm exposed to this much CO2, what are the the negative health implications of being exposed to this much CO2, acidification, nitrification? So they've taken this a step further and they do an endpoint analysis where they keep these all in a straight line still, and they say, how is this actually going to impact my health? So I'm really not wanting to do this here because this is a public health exercise really, but they can come up with units at the end, which is the daily, the disability adjusted life here, and say, because of this process, your life expectancy is going to be reduced by numbers, by probability, by a certain amount. So typically these numbers are really low. It's going to be 0.001 years. But obviously if I'm going to be reduced by 0.001 years because of your process, plus everyone else's process, it's obviously going to impact us all eventually. The last step, which I think is actually I've already covered, is the interpretation. So as I say, LCA is designed to be questioned at each stage. So it's easy to have numbers without much knowledge of their meaning. I think that's more than obvious. So it's meant to be iterative. So if you go up and down, as I say before, if something's wrong, go back up. If it's right, carry on. Question every stage. As an engineer, you should be questioning everything at every stage anyway. So I don't think you should need to be told to be questioning at every stage anyway. Not questioning in a negative way, trying to be constructive to improve this. As I've already said, this is it for the semester in terms of new material. This is not in the notes. The touch that I've given you is very simple. I don't think there's anything difficult in those first 3 questions. I'm not going to ask you any number type questions in the exam either. I do need to highlight though that bonus question. So it's a very new set of notes you'll see in the discussion that the notes there were released I think 4 years ago, but that's been under development for quite a few years. So it was only released late last year, early this year, I think. So it still might be a little bit, have teething problems. If you find anything that's good or bad about that, and if you do it, and I recommend you do it rather in the holidays after all your exams, not today, because I hear it takes about an afternoon, but I don't know. If you see anything good or bad about that, please let me know if you do it, because despite it being an international body that's put that forward, it was actually presented and it was put together by a group in Cape Town. So I know the group in Cape Town, they've asked me if we can get some feedback on it. Is it good? Is it bad? The voices are mainly American, I think, just to make it international, but you might actually spot a South African accent coming in there once or twice because of the people in Cape Town who couldn't afford the voiceover artists or just decided to do it themselves for that one little video.